Folks, I'm making this video at a request here to help you folks understand number 57 a little bit better. So my original picture here, here we've got our bullet. Move it along, and let's give that bullet a little color here. Make it a green bullet. Our bullet's moving along here, and it's going to impact this red block here that I'm calling mass B. And the bullet's going to become embedded into that block, and then the block is going to go sliding up the incline. The most important part of this problem is recognizing that when the bullet hits the block, there is going to be an external impulse acting on at this system right here. It's going to be a normal force. Therefore, momentum conservation cannot be applied along this direction. Actually, along any direction other than this one right here. So what I'm going to do here is I'm going to take a moment, I'm going to pause this, draw the impulse picture and the final momentum picture, and then we'll start talking about how to write the equations. Alright folks, I'm back here. I drew some more photos here that I want to talk about. So the important thing really is understanding what these pictures are saying. So what I've called picture 1 here, this is a diagram of my system before the impact. The system has a momentum to the right because the bullet's moving to the right. The momentum of the bullet is going to be MAVA1. Picture 2 is after the bullet is embedded into this block and the system is moving up to the right at some speed here that we're going to call V2. And then 1 to 2. This is the little thousandth of a second here time frame while the bullet is actually embedding into the block. The important thing to recognize here is that there definitely will be an external force acting along this surface, normal to the surface here. That would be an external impulse, which would be the integral f dt if we were to try to calculate it, but we're not going to. Now, additionally, there would also be a gravitational force vector, but I'm not even going to bother including that because that would be very, very small compared to this animal. So, momentum in picture 1, momentum in picture 2, impulse acting in between. Now, we don't know what this impulse is, but we do know that it's normal to the surface here. So what we can do is write an equation that's conservation of momentum in this direction. This direction momentum is conserved because there's no impulse here acting, because this impulse does not have a component in this direction. So what you need to do with this problem is take your momentum vector, your initial momentum, MAVA1, times cosine 30 degrees here would represent the initial component of momentum along this axis, equals your final momentum to get V2. Once you have V2, this object is going to be sliding now up this incline with some unknown speed here, but it should be slowing down under the influence of gravity and or friction if it's present. So just call this position 1, this position true. Write yourself a work energy equation. You'll have a kinetic energy here, a potential energy here, and if it says smooth surface, you would ignore friction in between it. If it doesn't, if it mentions something about a frictional coefficient, then you need to put a work term in for friction, and that's going to look something like minus F times D, whatever this distance is. And by the way, when you do the potential energy term, that distance, the height you need, can be written d sine theta, or this angle's theta. So that should be enough to get you through that problem. So enjoy.